Welcome to myprojectbuzzer.com. We are going to see the product for an active Marchand balloon and its application to a 24 GHz CMOS mixture. Next we are going to see the abstract for our product. The conversion loss of a down conversion mixer degrades overall receiver performances, and therefore active mixers with conversion gain are generally preferred. To date, Gilbert cell mixtures have become the most popular mixer topology due to its high CG and high isolation performances. The mixture incorporating artificial transmission lines and complementary transconductance stages exhibits wideband characteristics while maintaining a high CG. The mixture uses a negative circuit in its transconductance stage to enhance the CG. However, the two mixtures require off-chip balloons at the radio frequency and local oscillator ports to convert single-ended signals into differential signals in practice, and therefore the designs are both difficult to be integrated into a single-chip receiver. The mixtures incorporating cross-coupled pairs inside the Gilbert cell cores can increase their CG, but their on-chip balloons are still bulky. In our product, a fully integrated 24 GHz CMOS down conversion mixer incorporating an active Marchand balloon at RF port and a passive Marchand balloon at LO port is designed. Advantages of the active balloon are that the size can be reduced effectively and the loss is compensated. The active Marchand balloon uses CCPs to compensate for resistive losses and also to shape its frequency response, compared to the broadband or ultra wideband mixture that consumes high power. The mixture achieves a narrower operating bandwidth and high CG with low power consumption. Moreover, mixture features excellent isolations between RF and LO ports due to the on-chip balloons. The mixture is efficient. Next we are going to see the flow diagram for our product. The down conversion mixer is a modified double balanced Gilbert cell mixture. The mixture can be divided into 5 blocks: resistive loads, IF buffers, switch pairs, RF transconductance stages, and the balloons. Active loads can increase voltage headroom but suffer from poor linearity. Therefore, resistive loads are adopted in the design. Two common drain buffers are used for the IF stages because the IF frequency is from DC to several hundred MHz. Large transistors are selected to form the buffers. The switch pairs are controlled by the LO input signals, and the bias points of the LO transistors affect the LO driven power level for better CG. To make sure that the LO transistors can be easily turned on and off by minimum LO driven power, that LO transistors are biased near pinch-off regions. The transconductance stages are composed of transistors, and its function aims to transform voltage to current signals. The stage is a resistive feedback inverter consisting of an NMOS transistor, a PMOS transistor, and a shunt feedback resistor. Unlike a conventional transconductance stage in a Gilbert cell topology, the resistive feedback inverter amplifier is an efficient way to further boost the transconductance and then enhance the CG with a low supply voltage. The total transconductance of the inverter configuration equals GMN plus GMP, where GMN and GMP are the transconductance of the NMOS and PMOS respectively. Next we are going to see the output for our product. We design the circuit in the Tanner EDA. To create a new design, you have to click on the file and then give new and give the new design. You have to specify the folder to which you have to save your design. To add these components, you have to click on the add and then add the library file. Then for the new cell creation, you have to click on the cell and then give the new view and specify the name. Then you have to click on the setup and space simulation. Once the design have finished, then click on the setup and set and space simulation. Give the library files and specify the library file folder, and the at the last you have to type the TT. Here you have to add the generic library file for the nanometer or micrometer technology with the space and then give the TT. Then for the running time, you have to click on the transient Fourier analysis and give the stop time, maximum time step, print start time, print time step, and then click on OK. Then you have to click on the run. The output waveform will be created. Then for the power report, you have to click on the T-Spice and add the exported files. To export this design, you have to click on the file and then click on the export and give the export spice and specify the folder in which your design contains, and then the cell will be exported. That is, you have to add in the T-Spice. For that, you have to click on the insert command and then you have to click on the this toolbar simulation settings and specify the folder to which you have to save your power report file.